Hello, everyone, at Maple Conference 2021 from Melbourne, the most locked down city on the planet. One day I would like to get to Canada, but it won't be this year. However, the virtual conference, I pitched something quite a while ago, and it maybe went a little bit not quite to plan, but that's okay because I learned a few things, and I think there's the opportunity to maybe get insights from people who know more than me. So this work was inspired by different problems I've been orbiting around since my PhD days. And I learned something out of this exercise. We'll go a little bit through some definitions on types of state space model structures, which is essentially there might be an ordinary differential equation system such as this, the x dot, ODs with respect to time, state variables, inputs, and unknown parameters. And there's some observation equation which depends on those variables and parameters. And different forms of this are useful in modeling different types of problems. For today, we will look at a structure that's based on the uncontrolled linear time invariant structure. So it's this ODE system where you have a matrix multiplied by the state variable, and the output is a linear combination of these state variables. And there's different flavors of that. So you might have positive states and inputs and outputs, as you may have physical systems, and you also have that for the compartmental structures, which I've looked at with chemical networks, where there's conservation of mass, and that imposes certain restrictions on the basic structure. I have talked about structural global identifiability before. It's what I spent a lot of time on. We will just worry today about the broad picture, which is if you had an infinite record of error-free data and your model, is it possible in that idealized case to obtain a unique solution? And you want to be able to do that almost everywhere. So regardless of what the true parameter is, you want to be able to return that from your idealized data. And you may not have that property, and then you have to distinguish between solutions, or that may be impossible. So it really is an essential property to consider before going on and collecting data and trying to analyze it to estimate parameters. And there's different ways of going about the problem, which I won't go into here, but if you're interested, the background is there. If we're looking at the linear time invariant structures, one of the ways to go about analyzing those is the properties of the transfer function. And that we can take the Laplace transform of the structure equations, and we can obtain some expression, which in the uncontrolled case is essentially just a rational function. So that the evolution of the system would be a sum of exponentials, and that turns into a rational function in the transform space. And there are certain properties about that we can exploit, and we can obtain the coefficients of the transfer function for use in the identifiability test. But first, we have to check that the structure is minimal. And we can do that by checking for pole zero cancellation in the transfer functions. So one way of doing that is to factorize the denominator, obtain the poles, the zeros of that polynomial, substitute them into the numerator, and see if you get zero, in which case cancellation can occur or not. And that's fair, straightforward enough as a concept in the linear time invariant case. However, we're looking at linear switching systems, and I've realized that, like a bird entering a room, I've made a terrible mistake in loading up the theory here. But for today, we're just going to worry about that there is a switch, which is this gamma, and we have linear time invariant structures in effect at each time point, but the switch will determine which of a collection of those structures is actually in effect. And so each individual subsystem is just linear time invariant. We're looking at the uncontrolled case. And in our special case, the ULSS1, one switching event, then you either have one or two. So it's really just two coupled systems where the first system runs for a certain amount of time, and then you get another system, so with an abrupt switch between the two. The piecewise linear time invariant nature of the switching system, linear switching system, is what encouraged me to try and see, well, how much of that technology can we use in this problem? And we can kind of use some of the ideas, but we have to modify them. And because we have that coupling of one system into another system, then we don't have simple initial conditions for the second subsystem because it depends on the amount of the switching time. And so the state has evolved in the first part of the structure, and that communicates the sort of initial conditions to the second part. And so the rational functions that we would get by considering just the second subsystem in isolation, it's going to have complex time-dependent initial conditions, which are a bit of a pain to analyze. So we now have a very different type of rational function in that it now has time-dependent coefficients. But if we just look at the numerator, we can write it as a sum of exponentials in the setting that we're looking in. And then the problem is trying to recycle as much from the linear time invariant setting. Can we get the poles of the rational function, the transfer function, and substitute them in? And can we say something about whether this condition is satisfied or not? So we still have the same objective, but we have to go about it in a different way. I won't go too much into the application, but this was the sort of non-trivial case that I came across where we have different chemical species interacting. This one is present in a flow. This one is bound to a chip. This binds to this to make a complex. And then there's a conformational change of shape, and that produces a different form of complex, and there's transitions between these states. So it's not terribly difficult to write down the kinetics equations for this. It's the switch that makes things a little bit unusual. And that's because the experimental conditions change abruptly from there's a certain amount of this analyte A being injected through the flow cell, and then it changes to 0. And that switch delineates the difference between an association phase and a dissociation phase of the experiment. So we can use these relationships to pull out the substructures, which I call C1, the first, and then after the switching event, C2. And this bit is reasonably straightforward for linear time invariant systems. We want to obtain the state variables, expressions for those, so we can use those to define initial conditions for C2. And that's relatively straightforward, and Maple does a good job solving that quite quickly. As we come to C2, then we have a matrix for the dynamics, A matrix, which is just replace the analyte concentration with 0, and we set up some generic initial conditions. From the work I did for last year's Maple conference, I wrote some routines to analyze linear time invariant systems and put them together into a dashboard. So that should make it easy to use for people who are not familiar with this. And I'll get to reuse that because what I still want is transfer functions of linear time invariant structures. And here we have the numerator of the transfer function, which is like a rational function, and here's the denominator. So this, the complexity here we can see is because of these xi2 and xi3s. The poles that we're going to consider from that, the zeros of the denominator are here, and we would go through this process of checking for pole zero cancellation for each of the poles in turn. And here we've got the lambda 1 is clearly smaller than lambda 2. And as it happens, we can write just the numerator part of it, and we can see that if you were to set the trivial case of xi2 equals xi3 equals 0, then the numerator is equal to 0, so pole zero cancellation. But that's not a very feasible solution for us. It's not of any real interest because that would mean that you have no complex forms, which means there's been no dynamics of the first phase. In an experiment, we would expect something to form quite quickly. And so if there's no complex, there's no data to analyze. And so we can say, okay, we're not really interested in the trivial case there, but we're interested in for what other t might there be solutions. And I could find relatively easily that for the larger of the two negative eigenvalues of zeros, poles they are, then I could say, well, this condition can't hold, so we cannot have cancellation. Applying the same logic didn't quite work, so it was more laborious, but that's what gave me the idea of that it's probably good to have a a numerical check on any results that you come up with. So into the more the particularities of the problem is here we have an expression. We can see that the sums of exponentials in a reasonably complicated expression. It's only two exponentials and a constant, which we can try to rearrange and collect, and we want to make sure that it does satisfy the initial condition. But we notice that there are features that are just constants, so we can remove those because that's not changing the zeros of the expression. So we can, through a process of discovery, go through, okay, we can simplify this, which means fewer processes to complete, as we want to substitute in a whole lot of different randomly generated parameter values to test whether the solutions of the cancellation condition, that numerator we started looking at, which is now simplified. This, if anyone has any tips on how to go about doing this systematically, is ordering exponentials by the size of their exponents. That'd be nice. I did it for these two, but it might be nice to know if there was a more general way of doing it. And we extract these coefficients from that simplified numerator, and we'll return to those later. So the numerical exercise, so there's probably very inefficient ways of doing this, like I did originally with nested loops and not trimming out the constants that are not going to change the zeros. So I've set up some random variables, and we will just generate for each of these random variables all of the values that we require, which is n. We set the random seed, and we can make a matrix out of these and then convert that into a list of lists where each list that's an element is got a value for each of our parameters in theta, and we're giving the concentration of the analyzer value that we're going to use. And what we can do is set up a fairly simple function to solve, to apply fsolve, to solve this sum of exponentials, which now has all numerical values in it, apart from t. And we specify a range to look over that seems sensible given what the duration of a experiment might be, and we allow to go less than 0 in case there's some values that are slightly less than 0. And so then we might want to screen out when the case where fsolve does not return a solution. So sometimes that may be a null, and that's where I thought I was going to catch that with this line, but I wasn't able to deal with a null very effectively. So I created an empty set, and then you can check how many elements does the empty set have, and if it's 0, then apply a freeze. But I thought I should have been able to work with the null directly. So any tips on that are welcome. And also sometimes you may just get the function call back, and it looks like an unevaluated function call rather than some numerical value or list of those. So taking into account those cases, because we want to try and account for all of these calls, these 10 to the 4 calls of fsolve, there's a couple of helper functions there that just process the results and help us visualize them, which we'll skip over now in the interest of time. So setting some working digits, setting a seed, and then cranking through this to see, okay, how many hits do we get? How many roots do we get? We find that some reasonably large amount of the time, we don't get a solution from fsolve with 10 working digits. And just because I was curious by this, about this, I thought, well, let's look at the log 10 of the absolute value of the roots that we get, and they're clustered at quite small values here, around 10 to the minus 15 in absolute value. A couple of bumps over there. And then just today, a few hours ago, I thought, wouldn't it be interesting to see if there was any difference between the positive values and the negative values that are returned? And there's a bit of a difference. We might talk about that another time. So then you can repeat this process by saying, well, let's look at more digits. So now we have very few failures to solve for fsolve to return anything. And we get now that for 30 working digits, our roots tend to be, again, clustered close to around the value of the digit. So 10 to the minus 30 in general. And we can continue that just because it's fairly quick to compute with this code, even on a standard MacBook Pro. We can look at 70 digits, and again, we've got this progressive movement to smaller values of the values of the roots that we're finding out of our expression, solving of fsolve on our cancellation condition. So I did think that it was probably only the t equals 0 was the only root that we were going to get. And it was laborious to prove, but this seems to give quite good numerical support to that thought. However, we don't see that increasing the number of digits continues to decrease the number of failures of fsolve. And I did think, well, that's kind of interesting to me, despite what I started off doing. Why is that? And I thought, well, I used to do a bit more numerical work, and ill conditioning was something that rang a bell. So I thought, well, can we just, this is just a fairly simple modification of the above, which scales the equation by multiplying through by one of the exponentials that appear in the expression. And we can do the same thing as we did before with that modified function. We do see some decrease in the number of times the fsolve fails to return anything. And those are due to what we were trying to catch, which is the unevaluated function or the frozen empty set, which I was going to use to then recover the coefficients of the exponential. And if we were to look at the results in this case, so at the top we've got when we just use the original equation, and at the bottom is by applying that scaling, multiplying through by an exponential. It's difficult to compare. It'd probably be better to have these on the same scale. But this is very, very fresh work, so that's something that was beat me for time. And there's a little bit of difference between the two, but I guess this number being 200 times fewer failures to solve, we obtain a result more often with the scaled exponential. This suggests that there might be something to be aware of with the ill conditioning problem there, and that's something that I might look into and would be happy to take any direction from anyone out there. So back to the script. So this was all sort of started off about, I'm going to apply this numerical routine, and I'm going to get some idea about how this is going to inform the proof that I want to tighten up. And what we can do is just take those coefficients that were pulled off of the sum of exponentials earlier and just evaluate those at those beta values that were generated earlier, and look at the results that we get. And if we consider that, we can see that C0 seems to be positive all the time. C1 seems to take negative values, and C2, that seems to be positive. So that seems kind of a remarkable coincidence. And if you went through it, it turns out that C1 out of the 10,000 times is always negative, and C2 is always positive. So that is probably, if I'd known that, that might have given me a bit of a head start on a profitable direction to pursue for the proof. And I think I know how to make a nicer proof now. But it's certainly there's more than a coincidence there, you would think, and that might be something useful to follow up on. So even though the fsolve issues distracted me a bit, and I thought maybe I would get some nice pattern of coefficients that lead to fsolve failing, and that would provide some insights and maybe even a contribution to the Maple art category. I'm out of time for now, but if you're out there and you've seen me do something that you think you could make a comment on, I'd be very happy to have your input. Thank you for joining me today.